Hello everyone! Today we're presenting our second progress presentation for our Deep Visual Speech Recognition project. I'm Farah S Fahmy and I'm presenting with Hadeel E Mabrouk, Marian, Ramsis, Omar A Abougabal and Shahd H El-Ashmaw under the supervision of Dr. Nouri Sakr and Engineer Hesham Eraqi. Here is the outline of our presentation, as we want to share with you our progress and present our planned next steps for the coming semester. Moving to the project objective, we are tackling the problem of visual speech recognition that primarily depends on visual data. This can be used to build an accessibility application or aid in future research geared towards helping the hearing impaired better communicate back and forth with others, where our model can potentially transcribe what is being said. And now, Shahd will continue with the dataset descriptions.
We've decided to use the LRW dataset, which is a word-based dataset comprised of 173 hours of labeled data, of which 165 hours of those are for training and validation, and 8 hours are for testing. Each word is uttered multiple times by a diverse set of speakers from different genders and races. To arrive at our decision to use LRW as our chosen dataset, we first had to experiment with a few other alternatives, which we have since decided to exclude. LRS3 and LRS2 are sentence-based datasets, but since we've decided that our model will be word-based, these datasets are no longer a viable option. Next is the lip-to-wave dataset, which is comprised of unlabeled YouTube videos. The problem with this dataset is that it was extremely speaker-dependent with only a total of 5 speakers. Additionally, it was extremely large and took an extremely unnecessary amount of disk space. As for building our own dataset, we thought that that would be an unnecessary waste of time since there are already large labeled datasets like other LRW in existence, and especially since preparing and pre-processing the videos for our own dataset would take up a significant amount of time. Moving on to our evaluation of previous state-of-the-art models, our main goal in testing and retraining these models was to obtain a baseline of results that we could then test and compare our own model's performance against. Additionally, we wanted to see if they incorporated any elements in their architectures that might be useful to incorporate into our own model. The first model we looked at was the discriminative multimodality model, which achieved a benchmark on the LRS3 dataset. And what was particularly interesting about this paper was their use of the visual modality to enhance the audio modality, or in other words, using video data to improve the recognition of audio input. We thought it might be interesting to do something similar if we could potentially use audio data to enhance the performance of our lip reading model. Unfortunately, their extremely poor documentation of their code meant that we were unable to modify their model for our requirements. Additionally, they didn't publish pre-trained models, meaning we could not even test or evaluate their existing model's performance. Next, we looked at the lip-to-wave model, which implemented a sentence-based single-speaker branch, which was trained on their lip-to-wave dataset, as well as a word-based multi-speaker branch, which was trained on LRW. The main advantage of this implementation was their sequence-to-sequence level approach, which enabled the model to learn an implicit speech-level language model that supposedly helps disambiguate homophones, which are words that make the same lip movements but produce different sounds. However, with regards to their single-speaker approach, it was very speaker dependent and was not scalable at all for a large dataset of diverse speakers, which is our end goal, while their multi-speaker branch did not produce competitive results on LRW. As for the sentence-based transformer model, which achieved the benchmark on the LRS2 dataset, we were mainly intrigued by two aspects of their design. The first being their encoder-decoder attention and their external character-level language model, which, similar to the lip-to-wave model, might help disambiguate homophones. And the second being their utilization of the heuristic search algorithm BeamSearch for prediction. This incorporation of BeamSearch alongside the external language model showed a significant drop in word error rates. And this is just a simplified demonstration of the sequence that the model follows from the moment it is given an input until it makes a prediction. However, when the time came to train the model against our dataset, we noticed that the authors only published their testing codes, which initially wasn't an issue for us, but soon we noticed that they also made their code very tightly coupled, as well as purposefully manipulated and deleted big segments of the code that we actually required for the implementation of our own training loops. Additionally, we noticed some general issues pertaining to sentence-based models as a whole, mainly the fact that their datasets are inherently larger than word-based datasets, and that given our existing limitations on disk space, it would make matters more difficult for us, especially since pre-processing alone nearly doubles our requirements for free disk space. Additionally, due to the size of these datasets and our available computational power, pre-processing and training on average would take us around 3 weeks per test. And since we're probably going to have to run multiple experiments and tests, 3 weeks seems like a lot of time to waste per test. And as such, we have decided to forego sentence-based models as a whole. And Hadeel will now continue with the remaining models.
So the second model that we wanted to initially retrain was the TCN model that achieves state-of-the-art results on the LRW dataset, which based on our own evaluation of their pre-trained model was equal to 87.94%. This is actually quite higher than what was already reported by the authors, which we think might be due to further tuning that they already added after publishing their paper. Since it's a purely convolutional architecture, it results in a simpler training procedure. Also, the authors propose variable length augmentation technique in order to have a more robust model that can generalize well to variation on the sequence length. In addition to that, they also introduce a simplistic data preprocessing pipeline prior to the front end, which also contributes to the high accuracy score. This model was initially very promising, achieving benchmark results until almost a month ago when a new paper was published achieving a 3% higher accuracy score, which made us take the decision to exclude the TCN model and replace it with the new model that outperforms it, which we're going to further discuss in the coming slides. So the following figure visualizes the input data, where first the face detection and alignment are applied, followed by aligning each frame to a reference mean face shape in the transformation part. Then it gets cropped to a fixed 96 by 96 pixels wide ROI from the aligned face image so that the mouth region is always roughly centered on the image crop and later transformed to the grayscale. And as I mentioned, the previous paper was achieving state-of-the-art results until earlier mid-November when this paper was published achieving even higher results equal to 88.4% based on our own evaluation of their pre-trained final model and matching the results reported by them in the paper. What's pretty interesting about this paper is not the main building blocks as much as the smart refinements in the pre-processing and the front end, which largely plays a role in this state-of-the-art accuracy. First, in the pre-processing, the authors introduced mix-up as an augmentation technique by selecting two samples to generate a new sample using a weighted linear interpolation in both the ground truth and the loss function, which is beneficial since the models trained on the LRW dataset tend to usually overfit. Additionally, they also introduced the cosine learning rate scheduling, allowing for a decaying learning rate which potentially improves the training progress, and they also utilize label smoothing and word boundary for the learning process. We ran our own retraining experiments on both the base and refined networks that were introduced. Despite the time constraint and the relatively large time for training, which was around 90 minutes per epoch on average on the new machine, and despite the fact that each machine can run one experiment at a time at most, we were able to retrain both models with a smaller number of epochs, achieving results that are similar to the ones that are reported in the paper. So for the basic network, we ran 21 epochs with an initial learning rate of 310 power negative 4, whereas for the refined network, we were able to train it for a longer period of time, namely around 27 epochs with a smaller initial learning rate of 210 power negative 4. On this graph, we can see the main behavior of the accuracy over time, where the final model outperforms the base model by around 6%, and the final accuracy that the models managed to achieve are 76.84% and 84.5% for the base and final models respectively. We believe, however, that if we were to give further time for the models to converge, it would have led to even better results closer to the reported accuracy score. In addition to our model retraining and evaluation experiments, we also conducted further research on some related aspects. So first, we came across this inspiring model that applies knowledge distillation, making use of the dual nature of the audiovisual data, where the teacher model is a pre-trained audio-speech recognizer and the student model is the visual recognizer. These concepts were introduced for sentence-based models in a couple of recently published papers, where we can not only benefit from the audio data in training, but we can also leverage larger unlabeled datasets. As we can see in this diagram, the authors apply knowledge distillation by introducing a new loss function that, in addition to the base cross entropy loss, it further introduces three other losses added together, representing the KD on frame level, sequence level, and the context level. However, in our case, and since we're using word level dataset, that makes our problem more of a classification problem rather than having a sequence of words as an output, we can make use of only the frame level and the sequence level KD in our final design, as Omar will later discuss in further details. And now, Marian will walk you through further results of the research that we conducted.
As mentioned before, models trained on LRW tend to overfit, and considering the latest state-of-the-art model introducing mix-up, we looked further into different augmentation techniques and attention mechanisms to potentially incorporate into our design. The first being cutout. Cutout was shown to improve results in a previous model and works by randomly masking out square regions of input during training in order to improve the robustness and overall performance. Removed regions are replaced with zeros or random noise. The problem with this is that it might greatly reduce the informative pixels. The latest state-of-the-art model utilizes mix-up technique, which is when two samples of different classes are used to generate a new sample using a weighted linear interpolation. Motivated by mix-up and cutout, we have cutmix. Instead of simply removing the pixels like cutout, cutmix replaces the removed regions with patches from another image. Thus, there are no uninformative pixels during training, resulting in increased efficiency. There are many variations of cutout techniques, such as recap, which stands for random image cropping and patching, that mixes up to 4 images at once. This has shown great performance in benchmarks. However, we do not feel like it would be appropriate for speech recognition, as it is limited when the network is unable to capture the most discriminative regions, which is essential to us. Lastly, we have a tentative cut mix, which further develops on the cut mix technique. While addressing the aforementioned shortcomings and boosting the result of cut mix by a margin of 2%, this technique is reported to result in developing more robust networks that can attend to the most important parts of an object with better recognition. This is achieved by the utilization of attention maps generated from a pre-trained network to guide the localization operation of cutting and pasting among training image pairs. With regards to our research, since a tentative cut mix is still not well developed, it has only been trained and tested on image recognition, we are unsure of whether or not this technique can be extended to fit our project, or how long it would take to implement, or whether or not it will perform well with regards to our work. As such, we have chosen to forego the use of cut mix and cutout techniques for now and decided to instead incorporate spatiotemporal attention into our design. However, this might still be interesting to look into in future work. Attention is the process of adjusting or allocating activation intensity towards the most informative or useful locations of input. Attention mechanisms can be exploited to improve image classification and object detection. Different attention mechanisms have been used in various lip reading models. All of the excluded models had implemented some variation of spatiotemporality, so we think it would be a strategic move to implement our own version of spatiotemporality using C3D, since research suggests that multi-layered C3D models achieve better performance in temporal tasks. This 3CD model starts by focusing on appearance in the first few frames and tracks the salient motion in the subsequent frames. In our case, it would focus on the mouth and then track any motion happening on or around the mouth region. Now we will talk about some of the limitations that we faced during the semester that have influenced our design choices in regards to our architecture. Our main limitation was the needed computational power, since our problem is quite computationally demanding and it takes a long time to train a model from scratch. For example, on the newest code that produces the state-of-the-art results in LRW dataset, the time for one epoch in one of the thesis machines was approximately 5 hours, and to reproduce the results that were published in the paper, we'd need around 120 epochs, so it would take around 25 days to retrain the model. On the other machine, it was with higher specifications, it improved the time significantly, and each epoch was only 90 minutes long. But the machine can only handle one experiment at a time, as previously mentioned by Hadeel. Another limitation we faced was the availability of free disk space on the machines. The datasets that we experimented on are relatively large on their own, and they even take more space once the pre-processing is done. This was one of the primary reasons that we excluded tackling the sentence-based models, since their datasets are significantly larger. And finally, we took into account our limited time for our capstone project. to try and tackle the sentence-based lip reading problems because these models are quite heavy and they take around 14 days per experiment as mentioned in one of the papers, excluding the pre-processing time. And now, Omar will tell you about our design.
Now, we will discuss our research question. We will rely on the LRW dataset for our input as mentioned before. And according to our research and experimenting with lip-to-wave code, which outputs speech instead of text, we found out that the best performing speech models tended to be very speaker-specific and non-scalable over various speakers of different ethnicities and genders. So to gain good results, we need to train the model on an even larger dataset in order to learn more speaker-specific vocal traits, such as accents and tone. That's why we decided to go with text-based model. Earlier in the semester, we had a plan to go for a sentence-based model due to the fact that it would be better to implement a model that is sentence-based and can recognize phrases or sentences rather than isolated words, especially if we plan to implement our model as an application. Also, we would have then been able to incorporate a pre-trained language model like the BERT model or even an external language model to further leverage text-only data. However, as discussed before, we chose the word-based models because the sentence-based models are computationally expensive, and also because the last state of the art was introduced in 2018, and no one surpassed it until now, which made us believe that it's quite difficult, especially given the time and resources constraint we have. So we thought it might be better to initially implement our architecture design on the word level that can be later expanded to sentence level datasets. This is our design overview. We will try to improve over the state of the art by introducing spatio-temporal attention in the front end and by adding knowledge distillation in the back end. And I will further walk you through its details in the next slide. This is our proposed architecture design. Our model receives input in the form of videos, which then undergo a set of pre-processing procedures before moving on to the front end. The pre-processing consists of enforcing a word boundary, which means that only the word that we're interested in, which is located in the middle of the video, would be given the most attention by the model. This technique has proven to improve the results as mentioned in the TCNN's paper and the 3-layer bidirectional GRU paper, both of which were written in 2020. We also plan to incorporate facial alignment to our design in order to narrow down the region of interest by removing unnecessary background elements. The literature shows that the models that incorporate facial or lip alignment always perform better than those that do not. Additionally, mix-up augmentation, which has proven to improve performance as discussed previously, will also aid the performance of our model, especially since we rely on the LRW dataset, which has an inherent tendency to overfit on the data. Finally, we will convert the video frames to grayscale because the color will not affect the results, since the color do not provide any necessary information to the model, and also to remove it as a factor when training. We also decided to tweak our model further before moving on to the front and back end to include spatio-temporal attention mechanism. As mentioned, attention mechanisms in general have proven to be powerful in lip reading models. For the front end, we will have global average pooling, dropout, and squeeze and excitation, ResNet blocks, which outperform traditional ResNets due to their use of attention mechanism to model channel-wise relationships and enhance the representation ability of the module through the network. Lastly, in the back end, we plan to incorporate knowledge distillation to make use of the dual nature of the audio-visual data and bidirectional GRUs with dropout, average pooling, and a softmax layer. And now, I will leave you with Farah to discuss our future plans.
Now, I'm going to propose a list of expected tasks to be covered in the coming semester. We'll resume our model implementation and training by the 1st of March by adding the extra features of our proposed architecture to the baseline code we already have ready by now. And by the 1st of April, we will be doing hyperparameter tuning and testing against datasets benchmarks and begin writing our paper. Lastly, if we have sufficient time, we hope to further demonstrate our design, providing a proof of concept to our proposed model. Finally, back to our capstone reinforcement outcomes. Throughout the semester, we have researched different datasets and their representations, such as word-based, sentence-level, labeled and unlabeled datasets like YouTube videos. Additionally, we have looked at various components of our architecture, such as 3D CNNs, TCNNs, and multi-scale TCNNs, and furthermore, transformer and sequence models like long short-term memories and ByGRUs. Furthermore, we have considered using language models like the BERT model and knowledge distillation. Lastly, we have looked at regularization techniques such as label smoothing. We believe that, based on our proposed timeline, we will be able to have a research paper by the end of our journey, which we hope will have the potential to yield in a new benchmark in the automatic lip reading literature. Additionally, and concerning our secondary outcome, we hope that our research paper can potentially be used to build useful application, like an accessibility application among the other examples we mentioned earlier. Also, we have plans about making our paper code open source for other researchers and engineers to benefit from and build useful applications on top of it. However, until this point, our primary outcome is research. And here are our references. So thank you everyone, and we would like to give a special thanks to our supervisors Dr. Nouri and Engineer Hesham for their guidance and support.